All right, so now that we've discussed the basics of acids and bases, now we can move into a little bit more detail about particular acids and bases, and in particular, the strengths of some acids and bases. So in this section, we'll be talking about the strengths of acids and bases, and a lot of people get scared off by the naming, right? We talked about naming in the last section, and naming a binary acid just involves the hydro prefix and then the root and the ic and then space acid. The polyatomic ions, if they end in ate, they become ic acids, and if they end in ite, they become us acids, and that's about all there is to the name. So things that sound very strong, like phosphoric acid, it's actually a weak acid. Hydrochloric acid is a strong acid. Sulfuric acid is a strong acid. But until we get used to this idea of strong and weak acids, we really can't gauge the relative danger an acid might pose. Now, just because an acid's weak doesn't mean it's nothing to be worried about. There's a lot of organic acids that are in things like lemon lime soda, for instance, to give it that tartness that people like. And those do a number on the enamel of the teeth because, again, they're a weak acid, but there's lots of them, and people who consume that regularly will have issues related to that weak acid and what it can do to their enamel. So what does it mean to be a strong acid or a weak acid? Well, the strengths of acids have to do with how much they ionize, whether they're strong electrolytes or weak electrolytes. So strong acids are strong electrolytes. They completely ionize or close to completely ionize, nearly 100% in aqueous solution. So we show a single arrow when we show a chemical reaction for a strong acid. So HCl, for instance, completely dissociates into H3O plus and Cl minus. Weak acids, on the other hand, which are weak electrolytes, dissociate only slightly in water. So we show the double arrow to indicate it's an equilibrium process. There's a forward and a reverse reaction, and honestly, the reverse reaction is favored. So not much of the weak acid dissociates, mostly stays as molecular acid, and very little goes on to form H3O plus and then the anion of that weak acid. So that's the big difference. So again, it's just the extent to which ionization happens. In a strong acid, it's complete or almost complete. In a weak acid, it's usually very slight. Now, this is the end of the semester, so you've heard me say this before. I'm not a fan of memorization. I don't like to ask you to memorize things because I would much rather you understand than memorize. But there are some things that you just can't avoid memorizing. And the instance here are the 6 strong acids. So again, we could either try to memorize the millions upon millions of weak acids, or we can know these 6 strong acids and understand that any other acid is a weak acid. So our 6 strong acids are HCl, a strong acid, dissociates 100%. HBr, HI, also right in that same column. So notice we skipped HF. That's a weak acid, but HCl, HBr, and HI, those are half of our strong acids, right? So those 3. We also have polyatomics. So the sulfate ion gives rise to sulfuric acid, which is strong in its first step, and then strong for a weak acid in its second step because it is H2SO4. It does have 2 protons to lose. HClO4, perchloric acid, and then finally HNO3, nitric acid. Those are the 6, HCl, HBr, HI, H2SO4, HNO3, and HClO4. So everything else that is an acid is a weak acid, and an example of a weak acid here on this slide is acetic acid, a weak acid, mostly molecules of acetic acid and only very few acetate ions and hydronium ions in those solutions. Acetic acid, a dilute solution of acetic acid is your principal component of vinegar, your principal non-aqueous component of vinegar, about 5% acetic acid, 95% water, and most of us enjoy that sourness and things like salad dressing, but some people don't care for it, even in a safe weak acid like acetic acid's form. All right, so if we look at those strong acids, those are the ones I mentioned from before. HI is actually stronger than HBr, and HClO4 is slightly stronger than HCl, and then finally H2SO4, sulfuric acid, is slightly weaker than nitric acid, which is our weakest of the strong. Again, because they don't actually completely ionize, there is a slight difference, and that's how we can rank their acid strengths. If you think back to Bronsted-Lowry acid-base definitions, we have conjugate base coming from each of those acids, and the conjugate bases for the strong acids are essentially not basic. They don't do much interaction with water. But if we did want to consider them, the stronger the acid is, the weaker the conjugate base is. So even among the strong acids, iodide, the conjugate base of HI, would be the weakest, and nitrate, which is the conjugate base of nitric acid, would be the strongest of those bases. But again, they're all very, very weak bases because strong acids essentially only go one way, and we don't have a reverse reaction to worry about. It's that reverse reaction where we get the conjugate base behavior. All right, now if we look at the weak acids, which is pretty much any other acid, we have the conjugate bases can be fairly strong bases. Again, a weak acid can only give rise to a weak base, so they're not going to be actual strong bases, but the weaker the acid, the stronger its conjugate base. And ultimately, water at the very end, well, that's not really an acid, but again, its conjugate base, hydroxide ion, would be a strong base. Just like at the top, hydronium ion is actually a strong acid because it's what happens when strong acids dissociate, and then its conjugate base is water. So those two don't really fit well in this table. I'm not a big fan of how our text did this, but the other ones I agree with. So starting at hydrogen sulfate ion, well, that's a pretty strong weak acid. So the sulfate ion itself is a pretty weak conjugate base, although it is something people are concerned about. And a lot of personal care products now are sulfate free, and they advertise that because it is slightly basic, and people do have concerns about that. As we go down the list to much weaker acids, we get reasonably strong conjugate bases. So ammonium ion, for instance, NH4+, has its conjugate base ammonia, NH3, which is a fairly strong weak base. Again, still weak, but as far as weak bases go, not too shabby there. So the weaker the acid, the stronger its conjugate base. The weaker the base, the stronger its conjugate acid, and therefore so on and so forth. But again, the strong acids, their conjugate bases essentially don't act as bases. The strong bases, their conjugate acids essentially don't act as acids. I already mentioned the sulfuric acid having two protons in the first being essentially a complete dissociation and making sulfuric acid a strong acid, and then the HSO4 minus ion is a pretty strong weak acid because most of it goes on to form sulfate. But if we look at another case, carbonic acid here, H2CO3, is really a weak acid, and it's a weak diprotic acid. So it partially dissociates in water, giving up one proton at a time until it's finally carbonate ion. Again, because the carbonic acid itself is weak, most of it stays as carbonic acid. Very little goes on to form the hydrogen carbonate ion. And then that hydrogen carbonate ion, which is in pretty small amount to begin with, almost none of that will go on to form carbonate because it's an even weaker acid. So just be careful about that. Realize that, again, just because something has a lot of protons doesn't mean it's necessarily more dangerous than something else. HCl, for instance, is much stronger than H2CO3, even though HCl has just one acidic proton and H2CO3 theoretically has two, although it doesn't give them up very readily. Okay, now here is that sulfuric acid example. So sulfuric acid is another diprotic acid. However, this first step is complete dissociation. So carbonic acid was weak acid in the first step and weak acid in the second step. Sulfuric acid is a strong acid in its first step, but that hydrogen sulfate ion that it generates is present in very large amounts because essentially all of the H2SO4 goes on to form HSO4 minus as its conjugate base, but that conjugate base is a weak acid, and therefore it's an equilibrium process, although as weak acids go, this one does go pretty far to the right. but it's not a complete reaction. There is still a sizable amount of hydrogen sulfate left, and also a notable amount of sulfate left when we have this second dissociation go on. Okay, so we had our 6 strong acids, and then we said any other acid is weak. We do have some strong bases as well, and there's a neat trick on the periodic table where you can sort of make the letter B from our strong bases. So in group 1A, or group 1, the alkali metals, again, we can't consider hydrogen, but everything down below there, lithium, sodium, potassium, so on and so forth, all those group 1s would form strong bases as hydroxides. Again, we don't talk a whole lot about rubidium or cesium or francium hydroxide because they're pretty rare, so we tend to focus on the lithium, sodium, and potassium hydroxides as being our strong bases, but the others would be strong bases as well as hydroxides. In group 2A, the beginning, magnesium, we don't consider a strong base as a hydroxide, and really calcium sort of intermediate, and then once we get to strontium and barium, we get strong base behavior for their hydroxide. So if you look at the periodic table, you can almost make the letter B out of column 1A and the lower part of column 2A. So that might help you remember them. But the ones we tend to encounter in the course are lithium, sodium, potassium hydroxides from group 1, and then strontium, calcium, and barium hydroxides in group 2, although the group 1 tend to be more prevalent because, as we see here on the slide, there's pretty low solubility for a lot of those lower group 2A hydroxides. Okay, and we see our example of potassium hydroxide completely dissociates into potassium ion and hydroxide ion, and that's what makes it a strong base. And that's the behavior we would expect from any of these 6 strong bases, sort of to balance out her 6 strong acids. But realize there are more strong bases, and calcium is not such a strong base as our text may lead you to believe. Well, just like the weak acids having millions and millions of possibilities, there's also millions and millions of possibilities for weak bases. So essentially all the other bases, our slide here says most because we didn't talk about rubidium and cesium and francium hydroxide on the previous slide, but of course I did mention those, and those are the ones that would be the strong bases. So any other base would be a weak base, and they dissociate only slightly in water, form just a few ions, so this is a weak electrolyte and a weak base. And we see here ammonia mostly stays as molecular ammonia in water, but some of it will go on to form ammonium ion and hydroxide ion in an equilibrium type reversible reaction, as we see here on the slide. Now, we tend to have a lot of common household bases in household cleaning products. Most of our issues happen with either acids or greases, fats. As I mentioned, bases tend to feel slippery because they do work on triglycerides to break them down into glycerol and fatty acids. So grease stains or food stains, foods tend to be acidic, so you use bases to remove the food stains, and the grease, as I said, will react with the base to form glycerol and fatty acids. And then also hair will break down, and hair is often the responsible party for clogging drains, so that will open up the drains. And we see there's a number of weak bases. Ammonia is a common window cleaner. Bleach, sodium hypochlorite, the conjugate base of hypochlorous acid is our common cleaner there. Other laundry detergents, toothpaste, baking soda, baking powder, lime, we've got laxatives, so on and so forth, that can either be used for cleaning or cleaning one out. In the case of laxatives, we have a lot of bases represented. There's also some strong bases. Again, if you've got a clogged drain or caked on food stains in the oven, it's typically not possible to just take care of that with a weak base. A strong base like drain cleaner, which typically has a lot of sodium or potassium hydroxide present, that will again break down the hair and the other things that might be clogging the drain, and then allow for the drain to run clean once that blockage has been removed. So bases are very important and very prevalent in household cleaning products. Okay, so now that we've got a better sense of acid-base strength, let's pause here for a couple learning checks. Make sure you're really understanding these concepts. In the first learning check here, you can identify each of the following as a strong or weak acid or base. So first of all, identify if it's an acid or a base, then identify if it's strong or weak. So there's these 5 examples for you here. Go ahead and pause the video, decide if they're strong or weak acids or bases. Once you've made all your determinations, start us back up and we can check your work. Okay, so HBr, right, that was one of our 6 strong acids. Hopefully you remembered it. HNO2, you probably would guess that's an acid because it does have that H out in front, and since it's not one of our strong acids, HNO3, yes, HNO2, no, as far as strong acids go, you would identify this hopefully as a weak acid. NaOH was one of our 6 strong bases that we memorized, and therefore hopefully it was pretty easy to identify it as such. H2SO4, we're back to one of those 6 strong acids, so that is a strong acid. And then finally, copper hydroxide, copper 2 hydroxide, technically is a weak base, right? It's not one of the 6 strong bases that we mentioned, or the other few that might be in group 1A that would be strong bases as hydroxides, so therefore it must be a weak base. The hydroxide ion clued us into base, and the fact that it wasn't one of our 6 strong bases allowed us to identify it as a weak base. So hopefully you did very well with these. If you made a simple mistake, hopefully you understand that now. If you're still struggling and just not sure what's going on, please do try some extra problems and get in touch with me if needed. All right, so we have another learning check now, and you're looking at these acids. They're all acids, okay? And you're going to identify which is the stronger acid in each pair. So hopefully you remember the ranking, and obviously if you have a strong acid to choose from, then it's going to be stronger than a weak acid. So go ahead and make your identifications. If you need to consult that slide earlier on for everything aside from B, hopefully you can just guess at, but the other ones you might need that to make your determination. Once you've decided on all of these options, please do start us back up so that you can see how you did. Okay, so in A, HNO2 is actually the stronger acid. You'd have to have some sort of table or ranking for that. If it was HNO3, no problem. That's a strong acid and H2S is not, but I wouldn't expect you to just have memorized that HNO2 is a stronger acid than H2S. For B, that is fair game because we have HCO3 minus, the bicarbonate ion or hydrogen carbonate ion, which is a weak acid, compared with HBr, which is a strong acid. Obviously, the strong acid is stronger, so that one would be fine. Fair game for you. And then finally C, if you caught it, I did mention that H0 plus is how we tend to get our strong acids in solution, so hopefully you caught that and understand that would be stronger than H3PO4. Yeah, again, if you're having trouble, please do try some additional problems or certainly reach out to me for some help. All right, now I'm sure there are some of you out there that when I brought up reversible reactions, I bet your mind immediately went to the equilibrium constant, and you probably saw right where we were headed. So good for you. For the rest who have been just going along with the flow here, now's the time to hit you with some math because we really do have an equilibrium process in a weak acid or a weak base situation. So we have a rate with the forward reaction and a rate with the reverse reaction, and once we achieve equilibrium, those rates are equal, and therefore the equilibrium expression that we have here, instead of Kc, where it was the equilibrium constant with respect to concentration, we have a special form for acid dissociation constant, and that is K sub A. And if you'll notice, the K sub A removes the H2O, which is a pure liquid, and if you recall our discussion from last chapter about the equilibrium constant, it does not have pure solids or pure liquids present. So we have just the aqueous species, the H3O plus, the A minus, and the HA itself here in the equilibrium constant. So it's actually simpler than regular old equilibrium because we don't even have to think about it. It's always going to look like this, and that should make you happy, and that should hopefully make life easy. So let's look at a Ka for a specific weak acid. Formic acid, HCHO2, the acid found in bee and ant stings, is a weak acid, so it's an equilibrium process. The HCHO2 interacts with the water in an equilibrium, a reversible reaction to yield H3O plus and CHO2 minus. The equilibrium expression for this process, Ka equals, again, the H3O plus concentration times the CHO2 minus concentration. These are both very small values, but they are essentially the same. And then finally, the amount of unreacted, the CHO2, the formic acid that just stays as molecular formic acid, is going to be present in the greatest amount, and we end up with a Ka in this case of 1.8 times 10 to the minus 4. It is temperature dependent like all of our equilibrium constants, so this is at 25 degrees Celsius. So it's a pretty, actually it's a pretty large Ka for a weak acid. So formic acid is one of our stronger weak acids, but it is a weak acid, and now we have a number there. If I gave you Kas for weak acids, the larger the Ka, the stronger the weak acid. So that would be a way to help you out with something like our last learning check where you had to identify the weaker, stronger acid in a pair. Okay, so if we're looking at characteristics of acids, now we have equilibrium position. Strong acids are essentially completely ionized, so they greatly favor products. Weak acids tend to greatly favor reactants and mostly remain in their non-ionized state or unionized state. The Ka for a strong acid is very, very large, and then in the case of weak acids, they tend to be very, very small. And finally, if we look at the H3O plus and A minus concentrations, essentially it's 100% of the initial amounts for the strong acid. So we assume all of the HA concentration has gone on to make H3O plus and A minus concentrations that are equal. Whereas weak acids, only a very small percent of the initial HA concentration goes on to make the H3O plus and A minus. So conjugate bases of strong acids are weak, essentially not even basic at all, whereas conjugate bases of weak acids can be fairly strong, weak bases. Again, weak acids give rise to weak conjugate bases. Strong acids give rise to neutral conjugate bases. So here we have some acid dissociation constants. So these are Ka values that are from table 10.4. And we can see phosphoric acid has a Ka of 7.5 times 10 to the minus 3. It's the strongest one on here. And that's just the first step. The later steps for phosphoric acid, which does have 3 acidic protons, are much, much weaker. If we look down at the bottom, hydrogen phosphate, there's that last step of the phosphoric acid. That one has a Ka of 2.2 times 10 to the minus 13. So very, very little in the way of products, mostly staying as the hydrogen phosphate ion. And we see the dihydrogen phosphate ion is 3 from the bottom there, and it is 6.2 times 10 to the minus 8. So the first step is pretty strong for a weak acid, but the later steps are pretty weak. And then we've got some other acids in there. You can see formic acid is about 10 times stronger than acetic acid because of the 10-fold increase in Ka. All right, so acetic acid, as I said, we do consume. It's in salad dressings and other things, and it's, again, not an especially strong acid. 1.8 times 10 to the minus 5 is fairly weak, although appreciable ionization. If we wanted to compare them, again, I could have you compare any two pairs here, and you could clearly see why one would be stronger than another based on the Ka value. Larger the Ka, stronger the weak acid. Smaller the Ka, stronger the Kb of the conjugate base. Okay, so if we look at tables to get the actual numerical value of Ka, how would we write the expression for the Ka of something like hydrosulfuric acid, H2S? So first we'd write the equation for the dissociation of H2S, so H2S aqueous plus H2O liquid in equilibrium with H3O plus aqueous plus HS minus aqueous. So there we have our conjugate acid-base chemistry set up, and now we can say Ka equals H3O plus concentration times, instead of generic A minus, we can say in this case it's HS minus all over the concentration of H2S, our starting acid. Notice the H2O does not appear, it's a pure liquid, and does not appear here in our Ka expression. So hopefully you've gotten the hang of that, and you could write one of these if you were asked. Okay, so here we are. Now you're being asked. Here's a learning check to end this section. Your job is to write the Ka for hypochlorous acid, HClO. So if you remember our last step, first you'll write the equation for the dissociation of HClO, and then you'll set up the Ka expression. Pause the video here, do that work, and then when you're ready to check that work, please do start us back up. Okay, so that first step where we're writing that equation, we have the HClO aqueous plus H2O liquid in equilibrium with H3O plus aqueous plus ClO minus the conjugate base of HClO, and that's aqueous as well. So now we're ready to set up the Ka expression. Ka equals our products, H3O plus concentration times ClO minus concentration divided by our starting concentration of HClO, and then if it was appreciable, we'd have to consider it, but sometimes we would just consider that essentially none of it goes on, and we would take that concentration at the start to also be the equilibrium concentrations, but of course for a Ka, all of these values should be equilibrium concentrations. Hopefully that was easy work for you and you've had a good understanding of our concepts here in section 2 of chapter 10. If you're struggling, please do try some additional problems on your own first. See if you can fix it on your own. But if you're just spinning your wheels, things aren't making sense, please don't hesitate to reach out for help by contacting me. Okay, if you don't need help, if things are going well, then I will see you shortly in the next section.